All right, then. I did that quickly. Now, vertical. Is that where the denominator is 0 or the numerator is 0? Why? It's undefined. Okay, think of it as rise but no run is what makes a vertical tangent. Whereas horizontal tangent is run but no rise. So we need a 0 in the denominator. That's at y equals 0. Well, if you're lazy and looking for shortcuts, then you said, hey, there's 1, 0 there, so b, but why not that?
There's three places.
There's
three x values.
Yeah, you actually have to find all the places on the curve where y is 0, and there are 3. Y equals 0 yields 3 answers. Obviously, it's x. So 3. Okay? Do you understand? Cool. All right. Big lesson today. This is a humdinger. This is a humdinger. I think you'll agree at the end of this class that that was a humdinger. So, tricks. Yesterday we talked about how to do it. Now we're going to talk about how to choose tricks. 1 minus sine squared is an identity. What does it equal? Cosine squared. Okay. So if you ever see in an integral 1 minus x squared, then your choice would be let x equal sine. So you get 1 minus sine squared, and that's an identity. Okay? Tangent squared plus 1 is an identity. It equals secant squared. So if you see x squared plus 1, then you would let x equal tangent. So you get that tangent squared plus 1, and you replace it with secant squared. Same goes with secant squared minus 1, which is tangent squared. So if you see x squared minus 1, let x equal secant, and you'll be in good shape. Side note, cosine, cotangent, and cosecant could be used, and the only reason that we don't use them is because of the negative derivative. But they have the same basic ideas. There's still identities there. Just about everybody just uses sine, tangent, and secant as the main substitutions. All right? Unfortunately, however, sometimes things get a little more complicated than just 1 minus x squared. Sometimes things have a lot more junk going on. So in terms of general rules of thumb, if you see any number squared minus a function squared, think sum. If you see any sum of squares, think tangent. And if you see any function squared minus a constant, think secant. Now, if you are not a good memorizer, then don't worry. The minute you substitute, you will see in the next step if your substitution was good or not, because it'll yield an identity or not, and you'll know if you blew it. Okay? And you'll need to memorize this lesson less, and you'll just know what to do. But for now, let's use those as a blueprint. Would you tell me? Actually, let me do one with you, and then I'll let you go at it. Look at this last one here. Don't worry about the dx or the x squared. Focus on where either you have a sum of squares or a difference of squares. That's the start of the show. Okay? Because I have function squared plus some number, I should use tangent. Okay? So the idea is this is some kind of function squared plus constant squared is what I see there. With that, then, I'm going to make u what? Okay, if u is a tangent theta, then u is, what's a? Not 23, but root of 23. Okay? Tangent theta. All right? There's a little more to it than that, but we'll talk about that in a second. Actually, sorry, I want to change that. Not you. I don't want you. Forget you. I want to know, what do I do with the 3x squared? So, yeah, if u squared is 3x squared, then what's u? If u squared is 3x squared, u must be root 3x. Sorry, good job. Okay? That's your substitution unit. All right? Sorry, I didn't replace the u. That's the whole objective. All right? So that's the thought process. Go about it. Try the other three, and we'll go over them in a minute. 22. How much work he shows up to you, really it's the last thing that I would check for that needs to be right, because we're going to go way beyond this. And this will start to be intuitive and less memorization, write the pattern, fit the pattern. It'll just be, yeah, I know this needs to be 1 minus sine squared, so what do I need to do to make that happen? So you'll get there really fast. The first one, what'd you make your substitution? Y equals? Root 5 sine theta is correct. Okay? The next one is tangent. If you see sum of squares, it's tangent. In this case, then, the u is 5x, and a tangent theta is root 2 tangent theta. Okay? The next one is sine and secant get mixed up a lot because they both involve subtraction. It's just what's getting subtracted. When it's the function squared minus the number, it's secant. So you're going to use secant. U is 2x, and a secant theta is 5 secant theta. Okay. Now, if you were a little off, don't worry, because your next step will catch any mistake. You won't get a good identity if you chose badly. So now let's practice going the whole way. Yesterday we talked about how to do a trig sub when told what to do. Now you're going to figure it out yourself. We'll do one together and you'll try the next one on your own. All right, so when you look at that, x squared minus 9 is where you want to look to decide what trig sub to make. What kind of trig sub, or what kind of identity would be trig function squared minus 1? It's secant. Secant squared minus 1 is the identity we want to use. Then you need to work out the constant part of it. What's the substitution need to be then? X is 3 secant theta, I heard. Now, the first step will verify whether that did well or not. Do not do the dx and x squared first, because if you chose badly, you just wasted your time. You're going to have to do that anyway. Instead, go right to the square and say, does that make the identity? Because if it doesn't, then you're going to have to redo everything. So if I use that, then I get 9 secant squared theta minus 9. Will that clean up to an identity? Yeah, 9 will come out. Secant squared minus 1 is tangent squared, and we're home free. So that's going to work. That then means we can do the other pieces. dx, what will dx be? 3 secant theta, tangent theta d theta, and what is x squared? 9 secant squared. Okay. Here's where we still have some work to do. Cleaning up as quick as you can do without error. I could divide a 3 and a 9 out. I could divide out a secant. And then let me go inside the root. Inside the root, I'd have a root 9, or a 3, I suppose. And the root secant squared minus 1 would become root tangent squared. Again, kind of know yourself, how much you can do without causing yourself an error. Totally cleaned up then. What's the constant element to this? What's the final constant? 1/9, I agree. This actually cleans up quite a bit. How does it finally clean up? 1/9, just 1/9 cosine of theta. The tangent goes away. Secant in the denominator is just cosine. Okay? So, you are now home free. 1/9 sine of theta plus c. And now the stage of subbing back. Based on x equals 3 secant theta, x over 3 equals secant theta, you could draw a triangle there. Some people prefer to flip both and call cosine 3 over x, whichever you prefer, whatever you can draw the triangle from. But you need to find the relationship implied within. Adjacent is 3, hypotenuse is x. This, therefore, is x squared minus 9, which will tie into what you saw in the original problem. That almost always happens. You'll see some kind of form of what you used to have there again. Okay, so what is cosine of theta? Or, sorry, what is sine of theta is what I'm looking for. What's sine of theta? Root of x squared minus 9 all over. Okay, that's the process. Choose your trig sub, look for an identity, and if the identity is there, just proceed on like we did yesterday. Try the next one. wrinkle? Oh, it's kind of thinking it to my next step. Already, sorry. It should have been cosine squared. I was thinking of what I was going to do next there. Like that, sorry. Now what?
You separate it into 1 and secant squared.
1 minus secant squared.
1 minus secant squared or secant squared minus 1?
Oh, secant squared.
Okay. I guess I could have done that and separated it in 1. I don't know what I was thinking. Okay. So what's the antiderivative of secant squared?
Tangent.
Tangent. Theta minus theta plus c. And then, so x over 2 equals sine of theta. So, opposite hypotenuse adjacent. So, tangent theta is x over root 4 minus x squared. What's theta?
Arc sine.
Arc sine of, or inverse sine of x over 2 plus, okay? How'd it go? Okay, you good? All right then. A little wrinkle, but because you are the cream of the crop, at the cream of the crop, then this will go far. The problem is sometimes you'll see a integral that doesn't fit the old trig sub pattern. Now, just so we're clear, the trig sub pattern is square and square, either square plus square, square minus square, depending on where the function is, but square plus minus square is the trig sub pattern. Now you can see then that this is not the trig sub pattern, it's just one big fat square squared. So it doesn't really go there, but we can make that pattern happen by completing the square. Yeah. Yeah. Come on, you wouldn't even be in this class if you weren't good at something like that. Okay, so here we go. You will be fine. You'll say, oh yeah, that makes total sense. Okay. Oh yes, you do. Okay, so I think you'll agree that with the 11 there, this does not factor and definitely not into a perfect square. So push it off to the side, certainly because this is not a case where you could move 11 to the other side of the equation. That's not going to happen. Just push it off to the side, all right? Instead, put in that space which you want to be there to make a perfect square. What constant there would make a perfect square? Plus 9. Can you just go about saying, hey, I feel like I have 9? No, you cannot do that. You must keep the equation balanced, therefore, and then subtract 9. You can't really balance the equation because there's not an equation to be had. So it's an expression, add and subtract. All right? That then gives you the inverse, or not inverse trig sub pattern. What is that in brackets? The square of and square of. X minus 3 squared plus 2. Now you have square plus square. It is a trig sub pattern. What trig sub shall we use? What kind of trig sub do we use for square plus what? Tangent. All right. So what? This needs to be the tangent. Obviously, 2 we don't sub for the constant. So yes. I lost it, but there it's back now. I screwed up. Thank you. Okay. Now the trig sub. What do we do? Well, I definitely know x minus 3 needs to be a tangent of some sort. Okay. I'm going to start modeling the non-memorizing method. Okay. If I just did straight up there, would I be good to go, or would I need a little something? That right there would put me at tangent squared plus 2. Is that an identity?
No.
Not quite. So what else do I need in there? I need a 2 in there somehow, and it needs to really be root 2 so that when you square it, it'll be a 2. Now then, let's verify that that works. x minus 3 squared will be root 2 tangent squared plus 2 all squared. Before I do the dx, let's make sure that's gonna work. Is that gonna work? Yeah, the root 2 squared will be 2, which means I'll have a greatest common factor of 2 that I can take out. I'll get a 2 here and a 2 here, and I can get out, and I'll have tangent squared plus 1. Is that an idea?
Yeah.
It is. Okay, so we're good. We can proceed on. What's dx? Root 2 secant squared. All right. A little bit of cleanup. Pull the root 2 up front. That denominator factor, what will it be when that 2 is pulled out? Yeah, it'll be a 4. Be careful there. That 2 is squared that you're pulling out. That's a very common error. Okay. Inside then I have tangent squared plus 1, which is secant squared. You cool? Okay. What do we do now? Yeah, divide out a secant squared, leaving me with a denominator secant squared, which is cosine squared. How do I deal with cosine squared? You guys are not saying all right. It's not Yeah, that'll do. Okay. All right. How do you do cosine squared? 1/2 cosine 2 theta. Okay, so root 2 over 8, antiderivative, please. Theta plus 1/2 sine of 2 theta plus c. Really? Okay. Root 2 over 8. Theta I'll get to in a second. The problem now is that guy. I know theta relationships, not 2 theta relationships. So what do?
You separate
Yeah. By identity, sine of 2 theta is 2 sine theta cosine theta. And now I'm ready to do my substitution. I think way back at the top of the problem, oh man, that's a weird triangle. Okay, so what's tangent theta equal to, ratio-wise?
X minus 3 over 3.
X minus 3 over root 2. So opposite is x minus 3. Adjacent is root 2. Here's where it helps to have your kind of eyes wide open. What's the hypotenuse?
square root of x minus 3 squared.
Square root of x minus 3 squared plus root 2 squared. What's that equal to? Yeah. You'll see that original statement come back into it. Okay? So, x minus, I forgot what it was, x squared minus 6x plus 11? Is that what it was? Yes. Okay. Alrighty then, let's substitute. And then spike our pencils. What's theta? The inverse tangent of x minus 3 over root 2 plus, what's sine of theta? What's cosine of theta? Root 2 over that thing. Right, so I imagine in the answer book they probably have just a single x squared minus 6x plus c. I'd be ashamed to do all those in front for the c. That was okay. You with me? All right. Now, if you thought that was fun, whoa. Oh, you're gonna love this. Okay. This is one of my favorites. Okay. So, secant cubed, you're gonna love this. Kyle, I think you will like this the most. because you're constantly saying, what's the point of all this? Well, we are going to do something with absolutely no point whatsoever. Okay? You're going to love it.
So basically, first line run out.
Actually, it's got a point. It just feels like, what? I'm right back to where I started. It's so much fun. Okay? The big idea is to integrate seek and cube. Now, the first question that any thinking person would say is, seek and cube, who cares? Well, this is why you should care what seek and cube is. When you find arc length, you do an antiderivative of the root of 1 plus some derivative squared. Now, for the time being, rather than call this a derivative, let's just let that be some function. Okay? That then means when you do any arc length problem, you're often going to see that. Now, that doesn't integrate nicely, so you would trace that. What is u? If you have a sum there, what would you make u? Tangent. What's du? Secant squared. Okay, so you can see then that you would get something like 1 plus tangent squared in the root, secant squared. And so you'll get secant cubed anytime you do an arc length problem. It's not super duper clean and manufactured. Okay? So secant cubed is a big idea, although it seems like it's kind of arbitrary. It comes out as a big idea. Now, integrating this is a bit of, this is where the humdinger comes in. All right? Please, I'm talking to you, Mr. Fontaine, today. Please structure your work. If you want to understand this work later, it needs to be structured. That means you don't start in the middle of the box or over in the bottom right corner and just write all over the place. That's one way to think about it. Okay. Start in the upper left.
And then go directly to the lower right.
No. And you're going to work the right side of this problem, but the left side's going to come back. So you're going to see a lot of this is there, and I'm going to use it later. I'll explain that in a minute, okay? Now then, what's something you can do with secant squared? Give me something to do. Split it up. Split it up how? Secant squared and secant. Okay. Now, give me another idea of what you can do next. Do the identity. Okay, so that's exactly what I would have thought. You know, secant squared is tangent squared plus 1, and I can tell you from experience that goes nowhere. Okay, it gets you nowhere. So instead, it really, no matter what you try after that identity-wise, it goes nowhere. So somebody along the line, with their eyes wide open, said, well, it also kind of feels like a product of two things where one's not the derivative of the other, and that's kind of a nice antiderivative I could do.
You see it's a ultraviolet.
Yeah, so if you see it as an ultraviolet blue, that's the next step. If you let u equal secant theta d theta, or secant theta, sorry, dv is secant squared theta d theta because it integrates nicely. That implies du would be secant tangent d theta, and v is tangent. Upon ultraviolet voodoo, the ultraviolet is secant theta tangent theta minus the voodoo. What's the voodoo?
Oh, tangent squared.
Tangent squared, this is my favorite part, tangent squared secant. Okay? Good stuff. Now, at that point, you are nowhere. That equation is nowhere easier than the first one. It's pretty much just hard also. What can I do with that? Identity. Identity.
So secant and tangent.
What's tangent squared equal to?
Sine squared for cosine.
It's not 1 minus. Tangent squared is equal to secant squared minus 1. Okay? Yeah! Isn't that awesome? No. And when you do that, you get another secant cube.
The point is to make progress, though.
But we did.
No, we didn't.
Oh, we did.
It's circular. We just.
Yes, that's actually the name of this. It's circular integration.
Oh my
Yes.
What's the
point? The point is now you're 2 steps from being done. Maybe even 1.
Yeah, but there is no end.
Oh no, you're there.
It's
What can you do?
It's a geometric series.
Time doesn't work.
My tears will ruin the paper and make it all blue.
What can you do? Okay, I'll tell you what to do, but first, pause and appreciate. You just said that secant cubed is equal to secant cubed plus this graph. Something is equal to itself plus more. Isn't that crazy on its own, right there?
It's equal to negative.
You can't cross them out on both sides. What can you do?
In, say 2C2
Yeah.
equals confusing.
Yeah, move it over 2. So the other classman said, now we have more of it. Well, that's
We do.
actually okay,
That actually kind of makes sense.
because now we are home free. Assuming, and that's a large assumption, that you know how to integrate secant.
Yeah, that's natural law.
Natural log of, yes, thank you, secant plus tangent.
Why was this on
Yeah, that's my bad. Sorry about that. You probably had a real hard time with that. This was on last night's homework, which you, of course, could not do.
Yeah, I stopped for that there. I put a question mark.
Okay,
I got it.
we're not done.
What? No.
Well, the goal isn't to find what 2 of them are. The goal is to find what 1 of them is. Secant theta tangent theta minus log of secant theta plus tangent theta. The plus c is arbitrary, so I don't usually include it in the numerator. I just throw c. Now,
Are we ever going to have to do this as a definition?
oh wow, that would be terrible. And yet, totally expected because almost all arc length problems have limits. Oh.
I was asking to not do that.
Furthermore, they wouldn't even be clean. They would be, I assume, ugly. That's great. Hey,
What's wrong with me? I didn't want to do that by hand.
now I'm not big on memorization, but I'm also, I mean, some of you can't finish a test on time anyway. So to put that on it,
I should do a group test, right?
Yeah, we didn't do partner tests.
You promised.
yeah.
But don't do it alone.
Maybe I'll just have I'll just give one question and you can just do one step and pass it to the next person.
I'll just trade one check for the previous steps. What if there's a weak
I guess you all get a 0, or the next person's really in trouble. That would be fun.
You'd have to compare your experience.
No. Oh, okay. There we go. That's all the lesson. You should be good. Unlike last night's homework where you weren't good. All right. Do you have the one? What is it called? Review or something like that? Okay.
It's just like that same problem about like, is it so like, for it to be definite, it has to be, like, wouldn't it have to be geometric series?
When you
Like, because it keeps on adding beta.
But once you've done it once, you don't have to proceed. Yeah, so no, I assume what you're saying. But no. All right, I can't remember where I left off with you. Did I leave off somewhere like here? Here?
Yeah.
Fish?
We finished
21, we're done. 22, okay. Some of you, when I was grading these, you forgot your graphs. Many of you, when I was grading these, you forgot your domain or the direction of movement. Okay, those are all of those 3 mistakes together then resulted in maybe a 4th of you doing this completely correct. So make your corrections. Most people eliminated the parameter well here, which is good. Some people, myself included, then just out of habit said, all right, I know I'm supposed to do the domain and range here. Tell me why the domain and range for this problem aren't necessary. Yeah, it's an ellipse, so doesn't that equation alone rule out, hey, x can't be 5? I mean, I don't really need to say that. Hey, here's the graph, and by the way, x can't be 5. It's kind of redundant. That to say, I wouldn't take off if you had it. You typically do domain restrictions. This is 4, this is 3. The direction of movement. There are at least 2 ways to do direction of movement. One is to do successive points. For example, at time 0, where is the position? Or what is the position? -4, 0. Okay? At time, some nice time close to it, pi over 2. Where is it? 0, 3. What direction then is implied is clockwise. Now, just because it's calculus and it's because it's more fun, let's also do this in a calculus way. Say I looked at this point here, what is at time 0. What's dy dt?
dt is
3 cosine t. What's that at 0? 3. So if dy dt is 3, what does that mean? Y is increasing. Okay? And so it really must be going that way. And it wouldn't have helped to look at dx dt, because at that point dx dt would be 0. It's all moving vertically rather than horizontally. So a derivative helps you to determine direction of movement as well. This one, some of you need to make corrections on this one. Most people eliminated the parameter correctly. Do you have something like this?
Yeah.
Okay. I had a lot of people go on and distribute. I don't see why that. Why would you distribute and why does that help you? Why would you do that? Okay. What is the graph? Parabola is shifted. Right 4 and down 1. Now on the surface then it feels like this, but let's go back. If time is greater than or equal to 0, then can x be negative infinity? No, x must be greater than or equal to 4, and y must be greater than or equal to -1. You've got to restrict the domain and the range for good measure. And so that means it's not this whole graph, it's just here. And what's the direction of movement? As time gets bigger, x gets bigger, so we move right, and y also gets bigger, so we move up. Okay? Got it? Okay. Okay, this is one of my favorites. Whoopity-doo, whoopity-doo, whoopity-doo. Okay, this is cool for 2 reasons. First of all, we were talking earlier about the problem of the millennium kind of thing. There was a mathematician, I can't remember who it was. It might have been Bernoulli saw it. Some mathematician threw this out there as, how do you show this kind of movement? Actually, there's a second part to this movement here. And, no, take it back. This is the second part of the thing. Okay, so this is cool. It's called a cycloid. But why this is cool is this. Say you were here, and you wanted to get here in a gravity kind of motion, say like you were building a slide, okay? What's the quickest way, time-wise, not distance-wise, to get from there to there? What kind of slide would you build? You wouldn't go a straight line? No, shortest distance. The shortest time would be to get it going quick and then smooth it out. Now that is actually part of the cycloid. Okay? This is called a brachiostone, the brachiostone problem, or I can't remember, brachichrone, smallest time, I think. So there's Chronos in there somewhere. Okay, but at any rate, this famous mathematician threw it out there, and only the best mathematicians were able to get it. It's really cool. All right, this one is not really a huge idea of math, but I just like to say lysojuice. So I threw it out there. Lysojuice. Right. Something you know it. Okay. So you get the idea? It doesn't look like that, by the way. All right. But it was a lysojuice. There was like couple of these or something, right?
This is not.
Whatever. Yours weren't any better. All right.
These were so long.
So is Alan.
Wait, Alan, let me see.
Yours is better.
Let me see it.
Okay.
Wait, how's mine? Mine is not the worst I've ever done.
If the terms converge, that means the terms approach a finite limit. So when you prove convergence, you prove the limit exists. A numerical limit exists as the number of terms goes to this goes to E. Is E a finite number? It is. So the conclusion is convergence. Okay? Now this one got a few people, not all, but many. Okay? People say, well, what about that negative? It goes negative, positive, so it can't converge if it's constantly back and forth. But what happens to the denominator? Yeah, it bounces back and forth, but the denominator gets bigger and bigger, so it approaches zero. It's converging.
How would you
Okay?
Just be like,
You do not. N is discrete, not real, so its dot's not continuous.
Wait, so why is the denominator? Because it keeps.
Remember, the whole idea is you're listing a bunch of numbers, and as the list goes forever, do the numbers in the list start to approach a finite number. Now, as n gets infinitely large, like the 10th term, the millionth term, the billionth term, if you divide by the billionth term, then that means you're dividing by the square root of the billion. That's huge.
Yeah.
And you divide by negative or positive, divided by huge, is going to approach zero. Okay? So it converges. All right, this one, the inside goes to infinity, the numerator goes to infinity. This, in essence, then is infinity to the infinity. Does that approach a finite number? Most definitely not. It diverges. It most definitely does not go to zero. There's a way. Okay.
Oh, yeah.
Okay. This one has an alternating negative. I hope at this point you're starting to understand that if it has an alternating negative, it's one of those two, either negative 1 or negative n, negative 1 to the n, or to the n plus 1, depending on if you want to start negative or positive. Which one works? N. Okay, so you'd use n. The numerator, you could either say, hey, that's multiples of 4. I had some people say, hey, that's multiples of 4. But if you start at 1, does that work? No. If you start at 1, you're going to start with 4, not 40. So you need to tweak that a little. How can you? There are a couple ways to tweak that. You could add 36 to that. So when n starts at 1, you could also say 4 times. I want to start at 4 times 10, which is like, you can see how they're saying the same. Both are fine. What about the denominators? Straight up in. Okay? You might help yourself by saying n equal 1, n equal 2, n equal 3 above, just so you can try and make a connection between the n and what's there. Okay. N equal 1, 2, 3. The bottom's easy. What's the bottom? Negative n. I had quite a few people say 8n here. Yes or no? Which term fails? The third one fails. That does not work. Okay? So, instead, 2 to the n plus 2 works. What about somebody who did this? Does that work? Yeah. Yeah, that works. That's the same thing. Okay? Yeah, they're equivalent. So, that's it. Or one of those is the same. Okay? There are a couple different approaches. This, yeah, I just assume you say, hey, that's like sine stuff or cosine stuff. So yeah, sine. Okay, so these are pi over 4s, but what about the in-betweens? Pi over 2s, but what's pi over 2? But 2 pi over 4, right? So it's pi over. If you use cosine, if you were a teacher and some knucklehead, just to make your life hard, use cosine, what would it be? You could do n, I think n minus 2 would work.
It's a shift to higher.
Or would it be,
Plus or minus.
yeah, n minus 2. Yeah, n minus 2 would be.
Is that shifted by higher?
Okay, that's true, good point. Okay, last but not least, the old base problem. Some of you have the wrong idea. I understand you think right Riemann sum is always area, but it's not area. In this case, the problem is volume. So if you just thought of this as a Riemann sum of area, it's wrong. She estimated the volume by saying at 2, 4, 6, and 8, she measured the radius. Okay? And to estimate the volume, she kind of used rectangles, like using the right side 2, but a rectangle revolved, which makes a cylinder. And then she used the radius at 4 and a cylinder, radius at 6, cylinder. Okay? Will this right Riemann sum overestimate, underestimate, or you cannot say? You cannot say. Why mathematically can you justify that?
Because it's a cubic graph, you don't know, like,
It's not always increasing or decreasing. Yeah. Okay. So your work should look more like, is there a common factor besides the pi, obviously? Is the height a common factor? Yeah. 2. Last but not least, make sure you identify where you're getting your stuff from. So R of 2 squared. All right. Have a nice day. We will.
This one isn't deep.
Oh, actually. I think yeah, you figured I
wrote the other names on the other one, but that name's realized on.
Yeah, I got it.
Just one.
I'm just making it. What? What?
Yeah.
As long as you tried, dude.
Because I did.
Oh, what do you say it's due?
How do you do the proof for 25?
Yeah, exactly. Oh, that's great. Yeah, but as long as you have something. It's not due, fifth period didn't.
Yes.
Okay, because that's the only one I have.
a question about
The whole thing is.
I do not have the more stuff.
But it all makes sense.
Yeah, but I think
So you know that it's going to. So I don't
Yeah.
I like.
when they
I
ask
totally know.
like, what are your interests in how it's